In a chemistry class far, far away, Honors Chemistry Period 2 presents Molarity, The Acids Awaken, starring Courtney Crawford, Ashley Gunter, and Sarah Himebauch.
Purpose. The purpose of this lab is to determine the unknown concentration, the pH, the pOH of 3 different acids by titration.
Theory.
Titration is a technique used to find the concentration of an unknown solution by using a solution with a known concentration. Now, the titrant, or the known solution, is added from a burette to a known amount of unknown concentration solution until the reaction is complete. Normally, an indicator is used to show the end of the reaction or the end point.
Safety. For this experiment, an apron was worn to protect the clothing from acid spillage or base spillage. Also, gloves were worn to protect the hands, and closed-toed shoes were worn to protect feet, as well as goggles were worn to protect the eyes from spillage of the acids or base. For this experiment, it was not required for girls to wear their hair in a ponytail or a bun. However, it was highly recommended. First, the burettes needed to be cleaned when switching from one acid to another. The acid was rinsed through the burette 3 times to ensure that there was no other acid still present in the burette. Then the acid and the base were filled with their respective solutions. Each burette at that time was recorded with their initial volumes. Next, to a flask, 7 milliliters of acid was added as well as 3 drops of indicator. After adding the indicator, the base was released into the flask, constantly being swirled until it turned into a light pink color. Once the solution was light pink, the final volume of the base was recorded. This was used to determine how much base was needed to turn the solution light pink. These steps were repeated 3 times for each acid for all 3 acids. Data.
To find the average number of moles for the base, the formula molarity equals number of moles over liters of solution must be used. Because the molarity of the base is known and the volume is also known, you just solve for the number of moles. And once you have the number of moles for the base, it's equal to the number of moles of the acid because the chemical equation is a 1-to-1 ratio. Because now the number of moles are known for the acid, then you can plug in the number of moles and the liters of solution for the acid and solve for the molarity. But the molarity of the base is already known, so you don't have to do any work for that. For calculating the hydroxide ion concentration for the base, it's the same as the molarity because there's a 1-to-1 ratio for acids A and B. Then, to calculate the hydronium ion, you use the formula 1 times 10 to the negative 14th equals the hydronium ion concentration times the hydroxide ion concentration. And because you know the hydroxide ion concentration, you can find the hydronium ion concentration. And the same applies for the acid. For acid C, the same steps apply as acids A and B, except because it's a 1-to-2 ratio instead of a 1-to-1 ratio, when you're finding the number of moles, you have to, since you already know the number of moles of the base, you have to half the number of moles of the base, and then that will get you the number of moles of the acid. Then for the hydronium ion concentration, again, because of the 1-to-2 ratio, the molarity must be multiplied by 2. And then for the hydroxide, use the same equation as before, and you plug in what you just got for the hydronium to find the hydroxide.
The pH and the pOH can easily be found by using the hydronium ion and the hydroxide ion in acid A, B, and C. The pH and the pOH together equal 14, so you can simply plug in 14 minus pH equals pOH, or 14 minus POH equals pH. pH equals negative log hydronium, or PaOH equals negative log hydroxide. Discussion.
In comparison to 4 other groups who performed the same experiment, our data concluded to be fairly similar. In acid A, the molarity was always somewhere near 0.018. In acid B, the molarity was always somewhere near 0.013. And in acid C, the molarity was always near 0.0095.
One possible error made could have been that too much acid was released into the base, resulting in a bright pink solution instead of a light pink. This means we may have added past the endpoint.
Another possible error was that we could have read the meniscus wrong in our final volume reading on the acid burette and the base burette. This means that we could have mistaken a 7.2 for a 7.3, resulting in differences in our mathematic equations.